Well, hello, Honors Chem students. This is a video lecture that is meant to help you understand how to determine the voltage for a set of redox reactions. To do this, in this particular example, in question 5a, we are to first identify the charges of each species. We're going to write the oxidation and the reduction half reaction and determine the net voltage and determine if the reaction is spontaneous or non-spontaneous. The reaction will be spontaneous if the voltage ends up being positive, and if the voltage ends up being negative, it is non-spontaneous. So let's figure out how this works. First things we have to do is we have to determine the charge on the iron and the chlorine in this first example. This iron over here is elemental, so it's 0. This chlorine is elemental, so it's 0. And then we have this iron here ends up being a +2, and this chlorine is a -1. The way you figure this out is chlorine has to be the negative ion because iron can either be a +2 or a +3. So therefore the chlorine has to be negative. The only possible negative oxidation number for a chlorine is a -1. So if we figure this out, we can see that the iron is going from a +2 down to a 0. So that is what is being reduced. So writing that half reaction looks like this. Fe +2 plus 2 electrons turns into Fe0. The oxidation part of this reaction goes from 2 Cl-1s turning into Cl2 0 plus 2 electrons. Okay, so what we now have to do is, now that we've identified who's being oxidized and who's being reduced, we have to go to this new table. This is your AE reference table D. It's in your blue reference tables. Notice that this is a standard electrode reduction potentials. All of these half reactions in this list are all written as reduction because they all have electrons on the left side of the equation. Each one of these reduction half reactions has an associated voltage over here under this column labeled E sub 0. And what you will notice is that these voltages are the voltages for the reduction half reaction that is listed here. If you were to read these reduction reactions in reverse from right to left, they are no longer reduction reactions, but they are oxidation reactions. So if you reverse these equations, you then have to reverse the sign of the voltage. So let's see how this works. First of all, our reduction reaction is the iron +2 turning into iron 0. Now be careful because there are 2 iron reactions in this list marked here by the red dashes. And it turns out that the one we are looking at is this one right here. So the associated reduction potential for this reduction half reaction is -0.45. Now let's find this oxidation reaction. It'll show up in the reversed direction on this chart because they're all reduction half reactions. And so now we are looking at this reaction right here, written as reduction, but if we reverse it, it would be read as an oxidation reaction. So we're going to take that reduction potential, that positive 1.36, and we are going to negate it. So it becomes negative 1.36. So the total voltage for this reaction is we are going to add these two numbers together. And of course, when you add these two negative numbers together, you get negative 1.81 volts. It is not spontaneous because it is negative. It's a negative number. Okay? So that's all we're asking. What this means, if it's not spontaneous, that means this reaction will not happen in this direction. You will not get electricity to flow from this particular combination of chemicals. Let's take a look at part B. Let's start by assigning oxidation numbers all the way across the top. So we've got 0 for the copper and 0 for the silver. The nitrate is our spectator ion. It has a -1 charge in both of these compounds. And let's see, with the copper nitrate, there are 2 coppers with the one, oh no, I said that reversed, I'm sorry. There's 1 copper with the 2 nitrates. So this copper has to be a +2. There's one silver with this one nitrate, so this silver has to be a +1. So we can see here that it is the copper that is being oxidized. It is going from copper 0, turning into copper +2, plus 2 electrons. The reduction is starting from Ag +1, plus 1 electron, turning into Ag0. Now for these types of problems where you're just determining voltage, you actually don't have to balance the number of electrons. You really are just trying to identify the two half reactions. So we could balance this. We could put 2's in front of everything here to make sure that everything balances, but that's not going to matter when we go to our electrode potential chart. Okay, so I'm going to go over here and erase these marks that I made so we can see fresh what's happening for the problem we're working on currently. And let's see, if we find let's start with the reduction half reaction, the silver ions turning into silver zeros, we find that that reaction's right here. And as written, as this reduction reaction, it is a positive 0.80 volts. The other half of this reaction is the copper +2 reaction. Be careful that you're looking at the correct one. They're side by side here, but it is this one we want to look at, right? So it's written here as reduction, but it's actually happening in our reaction as an oxidation. So we have to take this positive 0.34 and make it, I'm sorry, we have to take this, positive 0.34 and turn it into a negative 0.34. So now we want to add those two numbers together. And when you add those two together, you get 0.46 volts. And this is a positive number. So because it is positive, yes, it is spontaneous. Yes, we can get electricity out of this, and we're just saying that because it ended up being a positive voltage. All right, pause the video, try part C and part D, and come back and check your work. So go ahead, pause it right now. So here's the answer to the third problem. Check your work. You should end up with a negative 0.34 plus a negative 0.76. With a negative 1.10 volts, so that is not spontaneous. It's not going to work in that direction, and with that particular set of chemicals. So, all right, let's go ahead and pause the video again, try the last problem, and come back and check. All right, go ahead and pause the video now. All right, so this last problem, you should have a total overall voltage of positive 0.62 volts. Because it's positive, this is a spontaneous reaction, which means, yes, you would get electricity to flow. You could power a device from this particular set of chemicals. All right, this concludes the video on how to determine the voltage from a redox reaction. There will be a couple other videos explaining the wet cell battery and how to label that wet cell battery diagram. All right, that's it for now. See you in the classroom.